In the previous lecture, we discussed that any function of a can be represented as n minus 1 degree polynomial in a, and we represented it as like this, and we said that for where A is a n plus n dual matrix, and we said that for m number of distinct eigenvalues of A, where m is less than or equal to n, we will generate a total of n number of equations by using this relationship. I'm calling this HFA. Using this relationship, we will generate n number of polynomials. So j varies from 1 to m, and L varies from 0, 1 till nj minus 1, where we said that nj is the algebraic multiplicity of their eigenvalue. Okay, so now we'll see some examples. We'll start with the simple ones and see how this can be applied. You can use a MATLAB program at the end to, or a Scilab code or an Octave code, whatever you are comfortable with, to verify, or a C code as well, to verify whatever we get here. So for the first example, let us consider a matrix E of the form 0, 1, minus 2 and minus 3. Okay, so if I take the determinant, so if you remember, determinants are also represented by this vertical bar. So if I take the determinant of this form, what I get is lambda minus 1 plus 2 and lambda plus 3. So this gives me lambda square plus 3 lambda plus 2. Okay, so this is my characteristic polynomial. So if I equate my characteristic polynomial to 0, what I get is that my eigenvalues are minus 1 and minus 2. Okay, I suggest that you verify this. This is what we get. Now let's say that for this matrix, okay, before we proceed, please note that algebraic multiplicity in both cases is equal to 1. Okay, and number of distinct eigenvalues that you have is equal to 2, which is also equal to the order of the matrix or the degree of the characteristic polynomial. Now let's say that we want to find what a power 10 is. So you have two options. I am giving you two options. One option is, of course, take 10 times the product of these two cross 2 matrix, or we resort to the method that we have discussed upstairs. So what we do is, we say that a power 10 is nothing but a function of a, and we say that this is equal to beta 0 I2 basically second order. In most cases we'll just drop this, assuming that whatever identity matrix we use is consistent with the order of the matrix under consideration. So beta 0 I plus beta 1 A plus beta 2 A square, right? No, will not have beta 2 A square because n is equal to 2, n minus 1, that is 1. So this is what we have, and this is what we have is h of a. Essentially f of lambda is lambda power 10, and h of lambda is nothing but beta 0 plus beta 1 into lambda. Now f of lambda evaluated at lambda equal to minus 1 is minus 1 to the power 10, which is 1 in this case. Similarly, h of lambda evaluated at lambda equal to minus 1 is beta 0 minus beta 1. So if we use this, what we get is beta 0 minus beta 1 is nothing but equal to 1. Similarly, we have f of lambda at lambda equal to minus 2, or h of lambda at lambda equal to minus 2 to be equal to f of lambda at lambda equal to minus 2, which essentially implies beta 0 minus 2 beta 1 to be equal to minus 2 to the power 10. Okay, minus 2 to the power 10 is also 2 to the power 10. So now we have two equations to solve for. Beta 0 minus beta 1 is 1, and beta 0 minus 2 beta 1 is 2 power 10. So if we solve this, what do we get? Beta 1 is, basically I am subtracting the second equation from the first equation. So I get beta 1 to be equal to 1 minus 2 power 10, and beta 0 is 1 plus beta 1 from the first equation is nothing but 2 minus 2 to the power 10. So what we have here is a power 10, which is f of a, is nothing but beta 0 into identity plus beta 1 into the matrix A, and now what we have is beta 0 to be 2 minus 2 power 10 multiplied by the identity matrix plus beta 1 is 1 minus 2 power 10 multiplied by 0 1. I guess A matrix was minus 2 minus 3. So what do we get here? This is the final matrix is of the form 2 minus 2 power 10. Then you have 1 minus 2 power 10. Then you have minus 2 multiplied to 1 minus 2 power 10. And next you have 2 minus 2 power 10 minus 3 times 1 minus 2 power 10. So this is what you essentially have as a power 10. Okay. If you want to substitute the values of 2 power 10, you can do that and finally get the values of this. But this is what you are essentially going to get. Please verify this. Okay. Please verify if this is correct. Similarly, let us take another example for the same matrix, and let us say that we need to compute e power at or exponential at. Okay, so essentially f of a, the function of a that is under consideration is this, because the order of a is 2 cross 2, so h of a is nothing but beta 1 beta 0 plus beta 1 beta 0 into identity plus beta 1 into a, and we have f of a to be equal to h of a, and if we solve further, so f of lambda at lambda equal to -1 is h of lambda at lambda equal to -1, and f of lambda at lambda equal to -2 is equal to h of lambda at lambda equal to -2. So these two give me the equation beta 0 minus beta 1 is nothing but e power minus t, and beta 0 minus 2 beta 1 to be e power minus 2t. So if I solve this, what do I get? I'll get beta 1 to be equal to e power minus t minus e power minus 2t, and I'll get beta 0 to be equal to e power minus t plus beta 1, which is 2 e power minus t minus e power minus 2t. Okay, so this is what I get. So using the relationship that f of a is going to be equal to h of a, I get e power at to be equal to beta 0, which is this multiplied by the identity matrix plus beta 1, which is this multiplied by the A matrix. If I solve this further, what I get is e power at is nothing but 2 e power minus t minus e power minus 2t. This is one factor. Then I have e power minus t minus e power minus 2t. This is the second entry in the matrix. The third entry is minus 2 times multiplied by e power minus t minus 2t, and the fourth entry is 2 e power minus t minus e power minus 2t, minus 3 multiplied by e power minus t minus e power minus 2t. I think we can solve this a little further, and we can express this as 2 e power minus t e power minus 2t. So the first component and the second component, there is nothing really to solve for. In the third component, I can write it as 2 e power minus 2t minus 2 into e power minus t. In the fourth component, I have 2, so this minus 3 and minus 2t, so I'll have 2 e power minus 2t minus e power minus t. So this is what e power at will look like when a is 0, 1, minus 2, minus 3. Okay, now let us take another example, and this time we'll consider a which is of the form 0, 1, minus 1, minus 2. So the characteristic polynomial in this case is given by the determinant of lambda minus 1, 1 and lambda plus 2, which is nothing but lambda square plus 2 lambda plus 1. So what I have is that lambda is equal to minus 1 is the eigenvalue with the algebraic multiplicity being 2. Okay, now let's compute the same e power at as we had done upstairs. So let's say we have this. So again, f of a is e power at and h of a is beta 0 I plus beta 1 a, and we have that f of a has to be equal to h of a for suitable coefficients beta 0 and beta 1. Now to find the coefficients, what we do is, since n1 is equal to 2 and this is of course equal to n, okay, so we'll use this, that we'll take the derivative of f with respect to lambda and solve it for lambda equal to minus 1 and equate it to the derivative of h with respect to lambda and solve it for lambda equal to minus 1. This will do for L equal to 0 and L equal to 1. N1 is 2, so 2 minus 1 point. Okay. So for L equal to 0, essentially you don't take any derivative. So f of lambda at lambda equal to minus 1 is equal to h of lambda at lambda equal to minus 1, which is essentially e power minus t is equal to beta 0 minus beta 1. So you get the first equation. For L equal to 1, d by d lambda of e power lambda t evaluated at lambda equal to minus 1 should be equal to d by d lambda of beta 0 plus beta 1 lambda, because h of lambda is beta 0 plus beta 1 lambda. Now this is essentially t e power lambda t evaluated at lambda equal to minus 1 should be equal to beta 1 evaluated at lambda equal to minus 1. Beta 0's derivative with respect to lambda is 0, so you only have beta 1. So what you essentially get here is beta 1 to be equal to t e power minus t. So this is your second equation. Now you can use both the equations to get what beta 0 and beta 1 is. In this case, fortunately, we have directly got what beta 1 is. So we need to find what beta 0 is. So we get that beta 0 is nothing but e power minus t plus beta 1, which is e power minus t plus t e power minus t. Okay. I'll use this small page to complete the derivation entirely. So e power at is nothing but beta 0 I plus beta 1 a, which you can possibly write as e power minus t plus e power minus t. Then you have t e power minus t. Then you have minus of t e power minus t. And then you have e power minus t plus t e power minus t minus 2 times I'll write it downstairs because I don't have any place, so minus 2 times t e power minus t. Okay, so if you solve this, I think you'll get it to be of this one. So this is what e power at in this case will look like. Okay, I suggest that you take other matrices possibly of size 3 cross 3 and try solving similar forms. Look for examples in the references that I have suggested in one of the previous lectures. You try to solve some from there to get a clear picture of this. Okay, so we'll stop here. Thank you.